I'm Chandra Saraf. I'm a postdoc at CASI. It's Korea Astronomy Space Science Institute. It's in South Korea. And today I'll talk about redshift bin mismatch in the context of S8 parameterization, the S8 parameter in using future cross correlations with LSST. So this talk summarizes 2 years of work that we did we started with Pavel Bilevitz, who is here in the audience, and my current boss, David Parkinson. So let's dive into it. So we all know about cross correlations, just kind of like a beginner's intro. If we have traces of this large-scale structure, they can be correlated if they overlap in redshift and they have the same angular selection, which means they overlap on the sky area. For example, CMB, galaxy surveys, quasars, H1 intensity, we have been hearing about from all day, et cetera, right? What I'm interested in, cross-correlating objects with known redshift. And when you have redshifts, you can do much better. You can divide it into redshift bins, which we call tomography. And the beauty of tomography is that you can study the time evolution of cosmological parameters, and this helps us constrain cosmological models much better. So for the rest of the talk, the tracer of my interest will be galaxies, and specifically photometric galaxies, where we have photometric redshifts, and we all know that they have errors. Now, due to these errors, the underlying true redshift distribution of the galaxies broadens, and this causes objects to scatter from one redshift bin to the other. It's been known in the terminology as interlopers, scatterers, however you call it. And this can change inferences on cosmological parameters, and what we basically try to do is to infer the true n of z using some self-organized maps techniques, or you have some stretch and shift parameters in the tomographic n of z, and you try to marginalize them over on terms of cross-correlation between redshift bins, so some of the standard techniques that exist. So the basic idea of all these techniques is to infer the true n of z for the photometric bin that we choose. The goal is to infer the true n of z. So we have shown in 2 papers that inferring just the true n of z is not the best thing that you can do. It will not recover the correct sigma-8 evolution. And why that happens is here. So if you have the set of power spectrum based on bins made on photometric redshifts, they relate to the true ones, but based on these quadratic coefficients. And in these 2 works, we showed that if you just infer the true n of z, these coefficients do not get accounted for properly, and that's why you get a bias. And when you have, let's say, cross-correlation with CMB, it's only dependent linearly, slightly better than the galaxy correlations, but still there is a bias in the inferred value of sigma-8, or S8 for that matter. So the key here is to infer these coefficients, P's, which we call scattering matrix. You collect them all together, and it forms like a matrix. I'll show you one later, and that's what we call it. Right, so in the 2 works that I was talking about, we showed that if you account for this scattering matrix, you can infer the correct evolution of sigma-8. For example, in the figure here, if you do the standard technique on these tomographic bins, you infer something like this blue dots. And once you account for this scattering of objects from one bin to another, you recover the red data points, which follows the fiducial evolution of sigma-8. Okay, but those simulations that we did was based on very simplistic assumptions. And here today, I'm questioning all the assumptions that I made on 2 years ago. So what we did was, we assumed very simple photometric redshift error distributions, let's say some Gaussian distribution, modified Lorentzian. So the goal there was that we create very idealistic, simple set of simulations to understand this scattering of objects. And so our photometric redshifts, however, sampling it was done from a known posterior. And the correlations were induced with the Flask code, which is the predecessor of GLASS, which everyone's using nowadays to get tomographic maps. So the simulation inputs were only redshift distributions and a known angular power spectrum. So the idea was, once you add errors onto the redshifts taken from this distribution, can we recover the evolution of sigma-8 correctly? Now here are certain challenges or problems that we've identified. First, was our photometric redshift distribution, the error distribution that we chose, whether it be Gaussian or modified Lorentzian, were they too simplistic and to infer these effects of redshift bin mismatch? Or the way we were generating photometric redshifts, were they adequate or not? We didn't know. And finally, was Flask inducing something? Because it's doing simulations in shells, so was it inducing some artificial features that was biasing our sigma 8? So for the rest of the talk, I'll be addressing these questions and trying to see what we get. So for the first one, we address them one by one. So first part is testing the effects of photometric redshift error distributions. So for this, we use the desk pipeline called RAIL, Redshift Assessment Infrastructure Layers. And we will talk about simulations correlated with LSST and Planck's. So RAIL, as I mentioned, Redshift Assessment Infrastructure Layers, is a pipeline which is designed to play with redshift estimation techniques based on the photometric capabilities, the observation capabilities of LSST. So what RAIL does is it samples redshifts and the 6-band LSST magnitudes from buzzard simulations. I think they have recently introduced some other set of simulations as well. With using RAIL, you can add errors onto the photometric magnitudes, which is consistent with the LSST technical document. So we chose errors consistent with the year 1 of LSST observations. So for example, here are the evolution of the 5 sigma depths from all the 6 bands that we have in our simulations, which is pretty much consistent with what we observe. Higher the magnitude, higher the error. And also to add here, these simulations also take into account the number of visits in each of the 6 bands that the LSST camera will make on the 16,000 square degree of the sky. So that's why one can see that the U band, the error doesn't scale as much as, for example, the R or the I band. Now, we estimate photometric redshifts using the pipeline inbuilt within RAIL called FlexGBoost. So we create specific training and test samples other than our photometric galaxies that we sample. We have separate training, validation, and test samples. So here is the performance of the photometric redshifts from the test set that we have, and it looks pretty neat. Sorry, let me go back again. Yeah, just to look at the error distribution. So the red curve is, so just to inform, this FlexGBoost gives us a point estimate, but also gives us a posterior for each galaxy. So just to look at the error distribution, how it compares. So the red one is when we have all the posteriors, you can stack them and have a look at how the error distribution looks like. And also, since we know the truth catalog, we can follow the true redshifts and compare the error distributions, and except for this very low probability density, we are in pretty good agreement. And this dashed line is basically the 5% line, 5% errors on the photometric redshifts, and we have 95% of objects sitting within this 1 sigma, this 5% interval. So we believe that our estimation of photometric redshifts is pretty good. And one thing that we don't improve is we still add correlations using GLASS, which is, again, a tool which allows you to simulate correlated maps over redshifts. And again, this standard analysis idea that we compute angular power spectrum based on these photometric redshifts. We bin them into 13 redshift bins. You can see them here. And we estimate S8 and galaxy bias, of course, because it needs to be estimated. It's a nuisance for this. So just to have a look at the 10 of the galaxy density maps, starting from, we have a redshift interval of 0.1, and it scales all the way up to 1.0, and then we have 3 more bins after this. Now, so I believe all of us know about the angular power spectrum. It's basically the distribution of power as a function of angular scale. And in these simulations, we have the CMB lensing convergence, and we have the galaxy density map. These are the correlation. So we have galaxy-galaxy correlation position, and we have galaxy and CMB correlation that becomes our observables. Now, to model the theoretical power spectrum, here I cheat a little bit. So lensing kernel is straightforward. Modeling the lensing auto power spectrum is straightforward. For the galaxy one, so in simulations, we did not use magnification. I'll come into it, why we didn't do that. And the key here now is the redshift distribution. So instead of using the SOMs or getting a stretching and shifting parameter, we follow the truth catalog, and we assume that we know what the underlying true redshift distribution looks like. We did this so that all the effects, all the uncertainties that come from inferring the true n of z goes away, and whatever remains is basically a bias coming from the tomographic bins itself. So before going anywhere, we should look if our validation, if our analysis pipeline is creating any systematics or not. So we analyze the maps before adding any photometric redshift errors based on their true redshifts, and we recover the sigma 8 evolution pretty robustly. So after adding the photometric redshift errors, of course, we don't expect the bias, galaxy bias, to follow the same underlying distribution. There is a mix of power from all different scales, so it can scatter very well. But now the sigma 8 follows a slightly different distribution. So the black one here is the fiducial evolution, and the red one is what we recover, inferring from the 13 tomographic bins that we have. And this gives us an S8 value of 0.792, where the fiducial is 0.832, following Planck 2018 cosmology that we use for our simulations. And this is very well in 3 sigma tension with the fiducial value. So now we have all very well known of the S8 tension that we exist in the cosmology, and this lies very well within the boundary of 3 sigma tension that we have, that we see from the various data sets in literature. And how does the auto power spectrum fit? Pretty well. We do not see any systematic bias in terms of the auto power spectrum that we are fitting, or also the cross power spectrum. The fits to the data points are pretty good. We have a very significant fit in all these cases. So I'm just showing 3 of the 13 bins here. Now we go back to the idea of redshift bin mismatch. So basically, again, I want to highlight that this is the problem here, that we have this quadratic dependence, and just estimating the underlying true n of z does not account for the exchange of powers between neighboring bins. And that's what our key understanding from here is. So we estimate the scattering matrix from the n of z, underlying n of z's that we have. So we estimate it independently and try to invert this relation and get the true power spectrum, or you can do it with theory and get corresponding theory for the photometric data set that you have. So scattering matrix basically compiles the information. So given a photometric bin, let's say photometric bin 1, 67% of the objects are where they should be. 28% of the objects have their true redshifts lying in the second redshift bin, and 4% in the third redshift bin, and so on. That's the information that we compute for the scattering matrix, and we invert this relation to get one of the data sets. And once you do that, not only the galaxy bias sort of becomes consistent with what the underlying true is, but also now sigma 8 follows very well the fiducial evolution. So the red one is now, after using the scattering matrix formalism, we go back up where they should be. And based on the scattering matrix, the S8 values goes to almost very close to what the fiducial one is, consistent within 1 sigma. So now the last question that we haven't answered yet is the wave of simulations generated with flask or glass giving us something which should not, it's not real, it's unphysical, and that's why we see this bias, and we need to do all this scattering matrix kind of approach. So now we move to the final step, which is using the Cosmo DC2 sims, which was prepared by LSST. So it's outer rim simulations, which is much bigger than the Millennium simulations that were done. It assumes a WMAP5 cosmology, where the sigma true is 0.8. There are objects up to redshift 3, and it's limited to a depth of 28. So it's the 440 square degree patch of the Cosmo DC2 sims. So we use only 300 square degrees out of it, and it has all LS6 filters, magnitudes, UG, R, I, Z, and Y. It also has redshift, position, and ellipticity, so one can play around with it more. And the desk community also prepared a photometric redshift catalog using FlexGBoost and BPZ for objects with I-band magnitude less than 26.5. So here we don't do anything. We just take their photometric redshift pipeline. We also take their simulations. So the uncertainty on our part that we were making the simulations are now gone, and we reanalyze this data in the same method that we did for our simulations. So we divide the galaxies into 13 redshift bins, but we only take objects up to limiting magnitude of 24, because higher than this, the redshift uncertainties increase, and they suggest that we should do only till 24 at max. Oops, sorry, the other way around. Yes. Again, we do not use any magnification sets in because our scattering matrix method that we have is not yet adequate to include magnifications. And we only use galaxy clustering data for now. And we fix, for our theory model, we limit to k range of 0.3 megaparsec inverse. And now we do redshift distribution in two different ways. One, very naive stacking the photo Z posteriors. We expect it to give wrong results already. And then again following the truth catalog, so assuming that we know what the underlying true n of z is. So here, if you can directly compare the two redshift distribution techniques. One is stacking n of z, which is the blue ones, and the true n of z. Following the truth catalogs, you get what is the red ones. So we should believe more the results that we receive from this true n of z, because that's based on the underlying truth catalog. So here I compared sigma 8 from the two methods, stacking photo Z posteriors. It's 0.739, way biased than it should be. But even if you use the n of z from the underlying truth catalog, we still get a 3 sigma tension with the value of 0.8. So we only receive 0.766. Unfortunately, I did not finish the analysis of this data set with the scattering matrix formalism to show you whether how well it gets connected or not. So what we are looking forward to is, we want to update the scattering matrix formalism to include magnification bias, and try it to see if the shear measurements get affected by this kind of systematic or not. Because again, we divide the galaxies into bins and before taking the shear measurements, and I believe the theory also includes the n of z. And if anywhere where we have this redshift distribution playing into account in a tomographic analysis, this kind of effect should show its impact. In addition, we analyzed one real data, which was the Legacy Imaging Survey and Planck PR3. These maps were prepared by Kenjun Hang in a 2021 paper. And we saw that if we do not use the scattering matrix formalism, the blue data points is what we get. But if we go from the way of computing the scattering matrix and computing sigma 8, we see what the red data points are, and we see that at high redshifts, we get a very good agreement with the ΛCDM prediction. So the goal is, again, to analyze more real data to see if there is some effect that can be counted for in the real data as well. Okay, to summarize that, tomographic cross correlations definitely will be very powerful with the upcoming data sets in terms of LSST, Euclid. And we have been finding apparent SI tension based on this redshift bin mismatch. And the year 1 LSST simulations that we made predicts a 3 sigma tension. And we believe that we have a better method called the scattering matrix formalism, which can correct for this bin mismatch. And now we are trying to look into the more broader picture, whether this can, to some extent, address the SI tension in cosmology that we have. So to finalize, this is the first image from LSST, right? If some of you have not seen. The first image that I had on my introduction slide was also the first image from LSST, which we saw yesterday, right? So thank you. Happy to take questions.
Thank you, Chandra, for your talk. Questions?
Hi. I know you said it a few times, but it's just late in the day and I'm getting a bit slow. What you're saying is that even if you have perfect redshift distribution estimation, for some reason your model doesn't reproduce the CL that it should. Can you explain why again?
Okay, so I'll try my best to explain to the knowledge that I have. Okay, so first thing, if we just have the true n of z, we broaden the redshift distribution because of the photometric errors. The true redshift distribution should be broader than the redshift band that we have, of course. But then it does not account for the neighboring bins, the information coming from the neighboring bins in it.
Sure it does. The estimated n of z contains the contribution from both bins.
Yeah. So what we are basically suggesting is there is a weighting for all of the n of z's that should go into account, and that weighting is coming from these coefficients that we have here.
Okay. I suspect that contribution is present when you actually empirically measure an n of z, but this is something that we can talk about over a drink this afternoon.
Yeah.
Hi, thanks for the talk. Could you comment a little bit on your error bars estimations? Because I would say they seem surprisingly small.
In this one or the later part, or all of them?
For this one, yeah, this one particularly, yeah.
I understand. For example, here the error bars look tiny. We believe that it is because we are assuming the n of z correctly, right? So we are assuming what the underlying true n of z is. So the constraint on the galaxy bias becomes much tighter because we don't have any extra nuisance parameters to play with, right?
But shouldn't because you're still using the photo Z that you obtained from the simulation, and that has a huge error possibility inside of it. Shouldn't that be propagated into the final error bar that you get?
I think yes, in terms of the covariance matrix, we did that because here, yeah, for these analysis, we had like 300 simulations, and we made the covariance matrix based on this sample covariance matrix that you get from 300 simulations. And also, for the second part with the Cosmo DC2 sims, it's only 300 square degrees of area that we used. In the DC2 sims, there is also a 5,000 square degree patch. So we use this 5,000 square degree area and a jackknife kind of approach to estimate the covariance matrix. So we believe that the covariance matrix should take into account the error bars that we have on the parameters, yes. So at the moment, we don't have any reason to suspect the error bars that we have, for example, here.
Okay, thank you.
Thanks for the talk. I just want to follow up on what Angus was saying. I thought you showed one case where you used the true n of z and it recovered the input, the truth.
So the true n of z's come, for example, here. So, okay, maybe this one, yes. So I've shown two cases where the true n of z doesn't recover. First is, here, this is without adding any errors. So this is assuming that we play with the true redshift sample. The tomographic bins are made on the true redshift, the underlying truth catalog that we have. So this is done to test our validation pipeline, that our validation pipeline is correct. So because if we are doing tomographic bins based on true redshifts, right, there is no source of uncertainty into the redshift, and we should actually recover the sigma 8 evolution very correctly, right? So so this is what is the pipeline validation that we have tested. And once you decide to move to sample based on photometric redshift, so basically now we are dividing into bins made based on the photometric redshifts that we have, and then we account for the redshift, the tomographic redshift distribution from the truth catalog. Then we don't recover the sigma 8 evolution correctly, and we find the S8, which is somewhat in tension with the case.
Okay, so in this case, your true redshift, in the case where it recovers, your true redshifts are kind of with straight line.
Yeah, exactly. So that is just done. So we just show this analysis so that to conclude that there is no uncertainty or there is no something spurious going on from the analysis pipeline that we have. Otherwise, we will recover something wrong here as well, right?
Okay. Let's thank Chandra for his talk on all the speakers today.